Just integrate it from phi1 of x to the phi2 of x, because that's what is the domain of y is. And then whatever outcome comes, you can integrate it from a to b with respect to the dx actually. Okay?
Sir,
Yeah.
but here in both sides the limits are functions.
Yes.
So in fundamental theorem there should be the function in just one limit, upper or lower. So how can we deal with these type of
What do you mean by upper and lower?
So in fundamental theorem of calculus, there is a function in just one.
In fundamental theorem of calculus, you also have functions. I mean, think about it. We put A star and B star actually, where the stars are the images. Wasn't that okay? So what was the second fundamental theorem of calculus statement, where you have a gradient field f, okay, A to B, and then you said that you can compute it along the curve C, where the C starts from A star and ends to B star. You can compute it as compute the potential at B star and compute the potential at B star. So these can be functions. I mean, in one dimension, haven't you done that? How to integrate a function from a variable limit, say g of x to h of x actually. Have you done something like this? It is also possible in one dimension. So you have what you call Leibnizian formula that allows you to calculate such kind of integral where even the limits are variable. In other words, you are not integrating from one point to another point, but from one curve to another curve actually. So you are doing the integration within curves. So I think this is calculus 1 stuff. Okay? So integrate. So the interpretation of this, or this can be interpreted as that you integrate the function, first with respect to y between these curves, and then with respect to x between the curves. Okay?
Yes.
So what would be the formula for type 2? So if S is type 2, so you're going to have also a similar formula, and the formula would look like that. Okay, if you want to compute S and dx dy, then this should be same as that you integrate f of x y with respect to dx, but from say psi 1 of y to the psi 2 of y, and x from say y from c to d. Have some kind of formula. Okay. So this is what Fubini theorem would say. So another justification, or what do you call a consequence of Fubini theorem, is that if your region is Fubini theorem, you are allowed to flip the limits actually in a suitable way. Okay. And flip the differentials actually. Okay. You can ask a question. Okay. The question is, this still doesn't defines this guy. This just tells you, this theorem just tells you that, okay, if you want to compute this object in a Fubini region, and when S is rectifiable, then that's a way to do it. But the question is, what is the meaning of this guy? Okay? But I would say this formula is a beautiful formula. Now this allows you to interpret even this guy actually. Okay? So let's get into the interpretation of this. That what is the meaning of this? Okay. See, computation is easy. Computation is not difficult. The real thing is making sense of the machinery, that why these definitions the way they are actually. Okay. Before going to the two dimension, would you like to tell me what is the meaning of an integral function, say for example with respect to f of x dx? How do you physically interpret this guy? Okay, that's something that we have memorized, area under the curve.
So summing up things.
The correction of points.
So what is the interpretation of dx, what is the interpretation of f of x, what is the interpretation of product of f of x dx, and what is the interpretation of integrating from it?
सर ये सम होता है रेक्टेंगल्स का
Small change.
You are again telling that. So it's like that. So it's like you have these rectangles, okay, delta xk's, and you can see this as a limit of it actually. Okay?
सर ये एरिया ऑफ रेक्टेंगल्स नहीं है
सर f of x हमारे पास होती है height सर.
Exactly.
d of x सर हमारे यहाँ variable होता है, height हमारी vary करती है.
Any height vary नहीं करता.
सर वो
X vary.
That's the, if this is a height, this is the length of really the tiny rectangle, width of the tiny rectangle, and f of x is their height, and their product is, so that's an area of a really tiny rectangle actually.
strip
It means
Really?
function up.
Really tiny.
Chopping it out in small as possible.
Yeah, which is this side.
Yes, sir.
Okay, I'm talking about this side.
Yes.
Okay, you reach to this by this chopping up stuff, but you can really interpret this as that. Okay, dx is representing, it's really a small chunk of, x-axis, which can be treated as a width. Okay, and f of x is like the height. How function high is going from, at the value of x actually. Okay, and then you're multiplying, and this is like a really tiny rectangle actually, like a line. Okay, and then you're summing up all these areas actually. So I'm saying, would you think about this actually? So now, keep this analog and think that what does this could represent? This
जैसे
ये region में area होता है.
area.
सर ये भी इस तरह से होगा कि पहले अब ये क्योंकि प्लेन में है ये, तो ये पहले इस तरह से x एक्सिस पे हम करेंगे इनको सारे को सम अप, और फिर y एक्सिस पे इनको सम अप करेंगे, तो इसलिए दो इंटीग्रल है.
So I'm interpreting dx as a width of rectangle and f of x as a height of rectangle, and I want to ask, what should be the meaning of dx dy?
सर x एक्सिस
dx dy.
सर x एक्सिस और y एक्सिस इसमें स्मॉल चेंज है.
स्मॉल चेंज है, मगर फिजिकल मतलब क्या है इसका?
सर एक छोटे से chunk का area.
It's a tiny rectangle.
छोटे से chunk का area.
It's a really tiny rectangle actually, really tiny, infinitesimally tiny rectangle actually. And you are multiplying value of it, f of x with it. So what is it going to be?
क्यूब सर.
So it's going to be really a cube. So it's a volume that you are summing up. Okay? So the dx dy is area, and f of xy is really the corresponding height of that region. Okay? So you can imagine it's like a a small strip or a really a rectangular thermometer or a strip actually. Okay, small. So whichever, but it's tiny its nature actually. The base is really small and it has some height actually. Okay? And you are saying, so what would be the interpretation of it? So that's a volume actually. Okay? But this was area, so now I can say, so that's a rectangle, but the rectangle under what? Function f actually. Okay, so I have a function x, and I'm splitting the entire area into such rectangles and then summing them back actually. So what would be the meaning here? So it's really analog actually. They are the similar, and this f of x is like what do you call a surface in region actually, a region in 3 dimension, and you are saying that can I find the volume under this region actually? Okay. So what you are doing is that you're splitting the entire domain of the function into small tiny rectangles. Okay, and then f of x dx dy is like the height of that what do you call it cubical shape. Okay, not necessarily cubical, but you can imagine that is going to be a cubical shape. Okay, and you are summing up all, and it's going to give you the total volume enclosed, total volume under this what do you call a surface actually. समझ आ रही है बात?
इसमें सर जब दो इंटीग्रल यूज हुई हैं, अब पहला इंटीग्रल किस चीज को शो कर रहा है?
देखा ना? So since you are, so here's the thing. अभी I'm getting into the description of it. So I'm just giving you an intuitive picture. I hope you got some intuition of it.
Yes.
So let's be a bit more precise and get into it that कि पहला इंटीग्रल किसे शो कर रहा है और दूसरा किसे शो कर रहा है. Okay? So see, what did you get? So first of all, this f of x y dx dy over s. So if I am in 3 dimension, now I'm going to make y axis here. That's x axis, y axis, and z axis. Okay, so s is where? So s is a region here. Okay, s is a region here. Okay, let's make a more coherent picture, something like that. So that's a region in 2 dimension. So that's my s, and it's a Fubini region. Okay. And then to each point of this region, I'm giving it a height, so it's going to be some kind of a region under the surface. And what basically, when you are computing this integral, what you are actually asking is that how much is this volume? Okay, so volume under this, this region. Okay. Now, what does this formula is telling you? Is this. Okay, so maybe if I redraw it properly, so this is the region in 2 dimension. It appears that it's Fubini type 1. It's not really Fubini type 1, it could be anything actually. Okay, but for interpreting this, I may assume it to be Fubini type 1 actually. For this, interpreting this, I may assume it to be Fubini type 1. Okay, because Fubini theorem says that it's Fubini type 1. And then this is going to give me, a surface. Okay, a surface. So I like to carefully draw. Really, so this line is going to be mapped here, and this curve is going to be maybe mapped somewhere here, and this line is going to be mapped to be something like that, and this is mapped onto, something like that actually. So this is like your region S, and this is really the f of S, the image set of S actually. Okay, and I want to compute the volume. So the question is, how can I compute the volume? So you may treat this as a cake actually. When you wake up in the morning, you बचपन में तो खाया करते थे हम सब, कोई खास किस्म का बेकरी से केक आता था. ठीक है, just interpret it. So take that cake, and the base is like the domain, okay, and the top is like the Fubini type region 1 actually. And I want to compute the volume of the cake actually. Okay. So the question is, how can I compute?
Slicing the cake in 2 ways, like this and this.
So the छोटे pieces में divide करते हैं rectangle.
So you can do it. So what does this definition is, or this result is telling you that you slice it into the really the vertical pieces actually.
Yes.
Okay. So I'm going to do what? I'm going to slice it into the vertical. So make the small slices and put them together is going to give me the area of it. So how to draw the slice of it? Okay. So let me show you the slice of it. It's really difficult to draw slice, but so the first of all, this is like your interval A to B, where this Fubini type region is defined. So this is like your A, and this is like your x equal to B. So this is really the line x equal to A, and line x equal to B. Okay, and what I'm doing is that I'm partitioning this line like we partition it, So this is like x naught, and this is like your x equal to x n equal to b, x1, and maybe an arbitrary piece. I'm going to give it a name letter. Okay. So let's take a.
मतलब सर यहाँ से एक प्लेन लेंगे, फिर उसको उस इंटीग्रेशन से सॉल्व करेंगे.
So the idea is this. Each of this is like a line actually. Okay.
Yes, sir.
Which is cross section. So it's like, this is like your knife. Okay. You are putting it in the bottom of, really the cake actually. Okay. And then you are moving it up. Okay? So if you take this line and slice it from the down or slice it from the top, so it's going to produce a curve here. Right? It's going to produce a curve here. And I can take another line and I can produce another curve here. Right? And this, so when I'm slicing it, what I'm going to get is really a piece of it. So how can I, you know, plot that? So, okay. So, okay. So I should go where? Ah, yes. So I should here. Okay. This goes here and this goes here. Can you visualize this picture?
Yes.
Yes,
So
yes.
this passes through the line. So it's really the
Double
slice.
slice.
Okay.
yes, sir.
So the question is, can I know the volume of this slice? So what should be the volume of this slice if I'm interested in computing it? So I need to know what is this. Okay. So what is this distance?
It's dx.
Sir, ये
So this is like your delta xi. Okay. So this is like your delta xi. Okay. Maybe you can see these are so small that okay, you can really visually see it here actually. Okay. It lies on one of the two partitioning points. Okay. So it's like your delta xi. In curves को भी नाम दें. So what should be? Okay. So if it is Fubini type region, then we should have. Okay. So what name should I give to this curve? So this is like your
phi 1
phi 1 of x, and this is like your phi 2 of x actually. Okay. So what would be the, you know, this area, the base of the slice? So what are you going to call it?
dy, delta y.
Huh? Delta y.
Phi
How are you going to interpret it?
Something.
Okay.
Z2 minus Z1.
So here's the thing. So I am taking this, okay, I'm taking this and slicing them up. So this is a curve. So if this is xi, what would be the interpretation of this curve?
Z of xi.
So it's going to be, so for example, if this is xi minus 1 and this is xi, okay, so this line is xi and this line is xi minus 1 and this line is xi minus 1. So what is this line actually? So I'm going to say this is f evaluated at xi, where y is allowed to move.
Yes.
Y is changing. You know, x is fixed, but y is changing too. Okay. And let's assume that this region is so small that this is the only value that you have in this small rectangle actually. Okay. So within that rectangle, you value तब्दील नहीं होगी. जैसे for example in one dimension, what we assume? So we assume that yes, this dx is, you know, of a really small size, but f of x is the height of, you know, the all points which lies here actually in this small region. Okay. So therefore I'm saying that this is a fixed f of x actually. Multiply with say dy, okay, and integrate where?
phi 1x to phi 2x.
Phi 1x to phi 2x actually. Okay, so phi 1x to phi 2x actually. You see it? So I'm integrating between phi 1x to phi 2x actually, this region. Okay, so it's going to give me. So this is giving me what really, what would be the interpretation of this guy? So the interpretation of this guy is going to be that it's the volume of this slice actually. Okay, so f of xi is like this height. Okay, so f of xi is representing this. All these points have the same value. I'm assuming it. It's so small enough that all these points have the same value. While you're multiplying it with, you're integrating it within y's actually. So it's going to give you the volume of this region. So what you should do next, you're going to say, take this entire domain and slice it into such pieces and bunch them up. Okay? So first you need to sum, okay, with respect to y over I equal to say 1 to, if these points are n, you're going to put n, okay, and sum them up over what? Each of delta xi delta. Are you getting the point? You're going to say, and then take the limit, okay, then take the limit, and if you're going to take the limit, this roughly n goes to infinity will also become an integral, which is going to be really the interpretation of it. Okay. So what does this guy is representing? So this guy is representing the volume of a function f, a volume under the image of a function f that is defined in a Fubini type region domain S1. Okay? And obviously, if this is equal to this, I can treat this as an interpretation of this double integral as well. Is it making sense? A little bit? So you can get to the pictures of the picture in the book is more clearer actually. So you can have a look and make sense of it. But I hope you got the essence actually, whatever I said. ठीक है जी. Let's do one example. Let's do one example. We do a non-trivial example. Okay. So I'm doing this example. So imagine I have a function f of x, y, okay, that is x over square root of 1 minus y squared, okay, where x lives between the interval 0 to pi by 2, where y lives between two functions, say minus sine x and cos x, okay. Minus sine x and cos x is dominated by these two functions. Okay. So this is the description of the region S domain of the function. Okay. You can already see that this guy has a bit trouble actually. Can you spot the trouble? So if I choose the points from this region S, so will there be a trouble making point?
Yes.
जब y पर by 2 होगा तो cos जो sin जो होगा वो 1 हो जाएगा
And
Zero
Then what
होगा,
is
zero
the-
होगा, so
you're gonna get in trouble actually. Okay. So if I plot it, how does it going to look like? This is going to look like this. This is the x-axis and y-axis. Okay. So I'm talking about the region x equal to 0 to say x. So x equal to 0 to x equal to pi by 2. Okay. X equal to 0 to x equal to pi by 2. So what would be the plot of y equal to cos x? So it's gonna go, so say this is the height of it, and then
1 to
it's gonna
0.
go down, something like that. Okay, and what would be the graph of minus sine x?
0 to minus 1.
Okay. So this graph is going to be something like that, but now since you are multiplying minus with it, so you have to reflect it actually. Okay. So it's gonna be reflection. So it would somehow look like this actually. Okay. How should I say? It somehow look like this. Something like this. It's not really precise. So I'm talking about this region. Okay. And this is the graph of the y equal to minus sine. So it doesn't look like it, but you may assume that this is the graph of it. Okay. Now the real troublemaking point here is going to be when x gets nearer to, what do you call, pi by 2 actually, then you have a possibility of explosion. Though this region is a perfectly Fubini type 1 region actually. Okay, and it's also rectifiable and it's bounded actually. I can find a rectangle in which I can fit in it. So it's bounded and it's rectifiable, and it's a perfectly fine region. But in this region, you have some points where the function can go a bit crazy. The question is, how can I, avoid those? So what we can do is that, okay, so instead of say considering this entire region, consider. So I want to stay away from the origin. Origin would also be a troublemaking thing, or origin would be fine.
No, so it will also, because cos of 0 is 1 and 1 minus 1 it will also.
So you're going to see that origin is also a trouble.
From both ends there is troublesome.
So the question is, let's get a little bit away from the origin, and let's get a little bit away from how much away? I'm really saying this is x equal to say epsilon. Okay. Epsilon is a tiny quantity. Okay. And what would be this? So let's call it x equal to pi by 2 minus epsilon. Okay, and I'm going to do the computation within this region, and in my final answer I'm going to take epsilon goes to 0. And let's see what we get. The trick is this. Okay, so you can avoid that discontinuity point actually. So how I'm gonna compute the integral. So I'm interested in computing what? So this is my region S, okay, or maybe original region is S and the current region is S epsilon, okay, to keep it, by S epsilon means that, okay, S that depends on epsilon, that is sensitive to the epsilon. I can really see it. I mean, if this epsilon is small enough, then the volume under the double integral of S and S epsilon would not be different actually. And we know it, for example, in one-dimensional integral. I mean, if you have, if you are integrating from A to B, a function, and even if you exclude A to B, is not going to make any difference into the area of the function actually. Okay. So I can really practically call it that this is really the S dA. Okay. So how can I compute this? I have say x over the square root of say 1 minus y square. Fubini theorem is are we in the assumptions of the Fubini theorem?
Yes, sir.
Is f continuous? Is f Fubini type 1? So everything is true for the Fubini theorem. That means I can apply the Fubini theorem here. And Fubini theorem tells you that yes, you can integrate it between dy and dx. Okay, where the y goes between sine x and cos x for sure, while the x goes from epsilon to pi by 2 minus epsilon. Okay, and now this is like integrating the Riemann integral actually, the one-dimensional integral. That's what it means. So can we compute it?
Yes, sir. It's easy.
We can compute it, not difficult. Okay. Can we compute the other? So you know how to compute the these one-dimensional integrals. So I'm not doing it. I'm just writing the final result, and the final result turns out to be pi square by 8 times pi by 2 minus 2 epsilon. Okay, so this would be the outcome of those two integrals actually. And then, if you really want to turn, for example, this S epsilon integral into S integral, so you need to take limit epsilon goes to 0. If you're going to take limit epsilon goes to 0, this will go to the, we'll get rid of this term and get pi cubed by 16, so this will be the area under the curvature. Okay, alright. So Fubini theorem allows us to interpret the nice functions, the double integral of nice function, as in the terms of iterated integral actually. Okay. So these integrals are iterated integrals. So you're doing the iteration of integral. I mean, if you integrating first and then integrating actually. While this is not iterated integral. This is integral in itself actually. I can, if I wish, I can just write one integral. I can write an S here actually. For example, what we do in electromagnetism. Okay, so there we don't write triple integral and
Yes, and
double
yes.
integrals. We just write integral, and by integral we can mean areas and volumes and all that.